Alright, so piggybacking off of that last video, what we're going to be doing in this case is we're going to be now assuming that we are the recipient of this scrambled message UKP and F. And what's going to be our goal is we're going to want to take that scrambled message and unscramble it. I want to actually know what that little secret message is going to say, so I want to do some operations to actually go ahead and find this thing. So in the fancy math lingo, what I'm going to be doing is I'm going to be building up some type of inverse or this secret decoder pen that I want to take and actually apply to that little string of 4 letters in this case. So the idea here is that I really should have something that's going to undo this operation. So if I think about what happened in my encoding phase, what I did is I took that letter M and then I sent it to the letter U. And that was going to be happening with this little function f. What's going to be happening now is I'm going to want to have some random function which is going to take that U and actually send it right back to the M. So the idea is that M is going to send to U, which is then going to send back to M underneath the inverse function. So in this case, there's a couple different ways you can denote this inverse. What I'm going to be using is actually the very terrible notation of f with this little -1. It's terrible because students always think about this as being 1 over f, which it is not. It is going to be properly an inverse. If it helps, you can think about the original function as being an encryption function. The idea is that I'm going to encode something. So I'm going to take M to U underneath the encoding function. And then what's going to happen is that my inverse would then be a decoding function. So it helps go ahead and use E's and D's. I'm going to right now at least use F's and F inverses so I can make the nice little connection to the world of all of the college algebra or algebra 2 or wherever you've actually seen inverses before, is that I'm not going to be doing anything different other than using some different operations that I have in this modular arithmetic world that you did not have back in that world of polynomials and things like that. So a couple really quick key facts that I want to rely upon and have in my back pocket as I move forward is going to be the notion of an identity, which I incorrectly wrote as inverses down below because I was all excited about inverses. So realize that these are going to look a little bit different than what I'm going to post down below or onto D2L in this case, because I'm going to change those from the incorrect word of inverse to identity. But I was already just about to hit record and I was like, oh man, those are wrong, but I'm already here and I'm already plugged in, so let's just go with it. So in this case, what the word is going to be the idea of an identity. And an identity in the world of mathematics is something that does essentially nothing. So the idea is that if I were to take, let's say, a 4, if I were to take 4 and add it to with a 0, what that's going to do is do absolutely nothing in the world of mod 26. 4 plus 0 is 4. So that 0 is then going to be referred to as this additive identity. I can add this thing and it does more or less nothing. That one's important, but not as important as the multiplicative variety. The multiplicative one is going to be this idea that 4 times 1 is then going to send myself right back to a 4. Multiplication by 1, again, essentially does nothing. So 4 times 1 is going to be a 4, and that's going to be in this mod 26 world. There's nothing special about the 4 that I happen to use there other than the fact that it's my favorite number. And the 26 is just the 26 that we happen to be working with over and over and over again, but that really can be any random n that I'd want to deal with, and the 4 can be actually whatever a you happen to fancy. Okay, so that's exactly what that fancy definition down below is introducing this notion of identities. The 1 is going to be the really, really important thing. The idea is that in order to actually find some of these inverses, I'm going to need to know some ideas that are going to connect to this world of this multiplicative identity. I'm going to have to actually find some inverses for things. And that's what all of this is going to cycle in on, is that this whole world of finding function inverses is going to boil down to actually finding inverses of numbers, which is something we've not actually defined before, but we're going to see that on this next slide. So fact 5.1.29 in this case is actually literally a copy and paste of what you see in my college algebra slides and things like that, is this idea of if I'm given some random function, how do I actually find its inverse? There's a little bit of formal notation that's going to happen, is that I do need to start with a function that's 1 to 1. What that means is that if I happen to have this case that M and let's say A both went to the letter U, this is not a 1-to-1 function. I cannot undo this thing, because what would U then go back to? The idea is that M made U and A made U. Well, if I wanted to do an inverse, would it go back to an M or would it go back to an A? The fact that I don't know how to answer that means that this thing is not a one-to-one function. What I want is this perfect match between letters going to themselves. So the idea is that if I have letters, they should make this nice little grid that's going to perfectly match up with themselves. So that's my first just formal starting place, is that my function needs to be one-to-one. All of these ciphers that we're going to be dealing with, at least from the initial point of view, are going to be one-to-one, which is going to say that I do actually have an inverse. What you do in this case is simply just a swap. That's all inverses are going to be doing, is that if my original function took x to y, my inverse then should take y back to x. So there's going to be a swapping of variables. And that's what step 2 is in this case, is that I swap my variables, and then the real meat of this argument is going to be to solve for that variable y. So in this case, what I want to do is I want to take that little cipher that I was dealing with on that last video, which I'm now going to write as y, which is going to be, in this case, this 3x plus 10 in this world of mod 26. So officially, this is my first step, is I have my little function. What I'm going to do in the second step is I'm going to take these things and I'm going to swap the x's and the y's. This is actually producing the inverse. The idea is that I now have x, which is going to be a 3y plus 10, and that's going to be done mod 26. So this thing right here is in fact the inverse. It just looks terrible because it's not solved for y. So what I want to do here is I want to take this little congruence and actually solve for that variable y. At the end of the day, that little y is then going to be my inverse, and that's what I'm going to go with as my actual decoding function. So classically, what I'm going to do here is simply solve a linear equation. I have a 10 that I'd like to get rid of, so I want to get rid of it. Here there are actually a couple different ways I can get rid of that 10. Most of the time when I ask students, okay, how do I get rid of a 10? Students immediately say, subtract 10, which is a totally fine thing to deal with, except for it's a little bit awkward because negative 10 is not necessarily an element inside of Z26 because it's not a number from 0 to 25. So it functionally works, though, if I want to keep myself in the world of having positive numbers that are going to be less than 25, I can also do this in a different way. And the idea here is going to be connected to this idea of how can I make the 10 into a 26, because a 26 is going to reduce down to a 0. So rather than subtracting 10, what I could do is I could actually add a 16. So the idea here is that this is then going to become x plus 16. And then on the right-hand side, what's going to happen is I get a 3y and then 10 plus 16. That's going to turn into a 26, which we know reduces down to a 0 mod 26. And that 0, again, is that nice little additive identity. So what I've done is I've found this very special number that when I add it to 10, it goes to 0. In that case, it's a 10 and a 16. So what I have on the right-hand side is a 3y, and that's still being viewed as a mod 26. So that's my first step. That's the one that students usually have no problems with. The idea is that they initially say subtract 10, and I say, yeah, that's great, we can subtract 10. We also could add 16. Really go with what you prefer. I like to avoid negative signs, so I'm going to do that as an addition of 16. The next step is what throws some students off, is that I now have this stage that I want to get rid of the 3. And here's where all of your years of mathematics is going to go against the grain in this case. Most of the time, students are going to say divide by 3, which is not what you want to do here, because in this world of modular arithmetic, we have absolutely no idea what division by 3 means. Have we ever seen a fraction in this problems or any of these things? The answer is no. Everything we've been dealing with is going to be some nice little subset of the integers. I've never seen fractions, so why would I want to start seeing fractions right now? The idea is that what does 3 halves equate to mod 26? I have no idea. That is really awkward to work with because all of this stuff is keeping track of remainders and things like that, so having a fraction makes really no sense at all. So that's the battle that we need to fight, is we need to think about another way to get rid of the 3. So the division by 3 is not 100% terrible. It's only 99% terrible as a guess, though there is some actual underlying properties that we're going to try to connect to. Officially, dividing by 3 is really like multiplying by 1/3. Because 1/3 and 3, those multiply to make a 1. And this is why division by 3 in your classic algebra setting kills off that little 3. Is because you have something that looks like a 3y and you divide by a 3. So the 3's go away, but they don't really go away like this canceling idea that everybody seems to use. What's officially happening is that 3 divided by 3 is going to make a 1, so you have a 1 times a y, which is simply a y. So that's the structure that I want to see, though I don't have this division, so I need something else. So the something else here is going to be connected to this idea of trying to come up with some number that I can multiply by 3 to make a 1. And that number cannot be a third. It's got to be something else. But what's special here is that I'm going to be dealing with this world of mod 26. So I have a little bit more information than I do in just kind of a classic algebra setting of x plus 16 equals 3y. That's viewed over all the real numbers. This is actually viewed inside of Z26. So I have a little bit more ammo to actually work with. So what I'm going to do in this case is I'm going to think a little bit about, are there any numbers that I can multiply by 3 to make a 1? And here, 1's maybe not the thing that I want to look for, but maybe something that's going to be congruent to 1 mod 26. So the idea is that not necessarily a 1, but maybe I could find a 27. If I could find a 27, I know 27 is the same thing as a 1, and everything would be great. So here I've artificially chosen the 3 to make my life pretty easy, because I know that 3 multiplied by 7, which I'm actually going to flip the order on, so a 7 times a 3, that multiplies to make a 27. Oops, I said 27. I lied all around. Okay, backtrack a little bit. Okay, a number that's going to make 27 should be a 9. I can do multiplication. So a 9 multiplied by the 3, that's going to make the 27. I was thinking all about 7, so I put the 7 in instead of the 9 and just decided that I'd multiply to make 21, and I was just going to go with it. But anyway, 9 times 3, that makes 27, and 27 is 1 more than 26. So I do know that this is going to reduce to a 1 mod 26. So this is the key fact that I want to work with. This little 9 is going to be referred to as the multiplicative inverse of that little number 3. And later on, we're going to be talking about different ways to actually find these little inverses. Right now it's just kind of a lucky guess and check. But later, when that 26 turns into an 8675309, good luck trying to find a number that when you multiply two things together, you get one more than some multiple of 8675309. That idea of guess and check is going to be essentially hopeless. So we're going to want a very nice systematic approach to actually finding these things. Okay, so now that I actually know that 9 times 3, not 7 times 3, makes a 1 mod 26, what I can do in this case is I can multiply both sides by a 9. So on the left-hand side, I get a 9x plus 16, and on the right-hand side, I'm going to get a 9 times a 3y, and that still is again viewed modulo 26. Over here, I see the 9 times a 3, which is going to turn into a 1, and a 1 times a y is simply just going to turn into a y. And that again is viewed mod 26. And on the left-hand side, there's a couple different things I could do. I could either leave it directly like this, so 9 times x plus 16, or what I could actually do is I could do the distribution and clean things up a little bit. So I could either stop right here, but I'm going to choose to go a little bit farther just because the function's a little bit nicer to work with once I've done the distribution, because then I don't have to do it constantly over and over and over again. So distributing the 9 is going to give me a 9x plus a 9 times 16, which in this case is going to turn into a 144, because I can actually do multiplication now. And what's going to happen is I still have a y on that right-hand side. Again, everything is done mod 26, so that's what's going to happen here is that I don't have to touch that 9 at all, but what I could do is I could deal with that 144. 144 reduced mod 26 is actually going to turn into a 9x plus, in this case, a 14. And there's going to be a y over there, and that's mod 26. So I'm going to work with this one because it's a little bit nicer because I don't have to constantly do that distribution over and over and over again. So that very last step, I guess if I go back to my college algebra notes, that was step 3. Step 4, which I can call as a 4, is going to be to take this y and then identify this thing actually as the inverse. So in my world, I'm going to say f inverse of x. So it's going to eat some x, and now it's going to be identified as the 9x plus 14, in this case mod 26. So I have my encoding function, which was my function f, and now I have my decoding function, which is going to be given by this function f inverse. What's nice about this is that once you have this thing, here's my actual algebra computation. Once you actually have this thing, you can then run that exact same argument to see if it's actually done the decoding process successfully. So I can take that message UKPF, which was that secret message, quote unquote, that I've actually received. I can feed it those numerical equivalencies. The idea is that U is 20, K is 10, P is 15, F is 5, and then feed those 4 little numbers into my inverse in this case, and see that it's going to kick out those numbers 12, 0, 19, and 7, which we know connect back to that letters of math, M-A-T-H. So my function does exactly what it's supposed to. The idea is that my original function, f, took m to u, and now my inverse is going to take u and send it back to m. So there's a whole bunch of questions that come into play after this. And I said early on that this particular function in terms of actual security and application is complete rubbish. There's really no actual application of this thing other than it serves as a very nice springboard to introduce some notation and some terminology and make this connection a little bit more formal before we start talking about some cool things. But there's at least kind of a couple little laundry list things that we can talk about now. So the couple key things that we had to do in this particular problem was we had to find this special number y that's such that when we multiplied it, it made a 1. So that's going to be this idea of finding an inverse, a multiplicative inverse. In this case, we could randomly see that a 9 multiplied by a 3 makes a 27. That's not always going to work so nicely. Randomly guessing things is usually not the best approach to things, so we're going to want an algorithm to actually find that. Conveniently for us, there actually is a very beautiful algorithm called the extended Euclidean algorithm that's going to do just that. So we're going to see that in a couple sections, and it's a pretty slick little way to actually identify these inverses. A component of that thing actually answers the second question, is the idea is that, is this little affine cipher always going to work? What happens if I change the 3 in front of the x to something like a 2 or a 4? Well, if you think about it, what's going to happen is that if I have a 2 out in front of something, regardless of what I multiply that thing by, my output's always going to be even. So there's no way that I'm going to hit all of the numbers in Z26 because I'm only going to be picking up the even ones. So the idea is that there's going to be no way that I'm going to send something to a 15 because I'm multiplying it by that 2 always. So there's a problem when I start to have some of these little weights out in front of those things as being even numbers. And the even issue is actually connected to what the factors of 26 happen to be. The factors of 26 are 2 and 13. So what's going to be problematic is anything that happens to have a 2 or a 13 in it. So what we're going to want to see is we're going to want to live with things that are going to be referred to as relatively prime. And that's a piece of terminology that we're going to see in a couple sections, but it's at least worth mentioning at this stage as I kind of get into that case, is that you're going to hear some of these pieces and it's going to be exactly addressing these issues of there are some times that problems come up. There are times that problems don't come up, and those are going to be the cases that I'm going to want to see. So that's the idea, is that we don't always have this working, which is both good and bad. I just have to choose things correctly to make things work really nicely. And then the last and really important question is, how secure is this thing? And the answer is very, very much so a no. It's not secure really at all in this case. The idea is that you can actually come up with a really pretty quick brute force attack to this thing. If you use that code that I showed you in the last video, and I'm going to cycle back to in just a second, and start thinking about just plugging in any random function f of x, which is going to look like an ax plus b, well, there's really only 26 options for the a, actually less because of this issue that I just mentioned above, and there's really only going to be 26 options for the b. So if you make a loop that's going to cycle through all of the choices for A and all of the choices for B, which is going to give you at most 676 loops in this case, if you look at all of those outputs in this case, so 600 of them, which sounds like a lot, but it's really not that bad. If you skim through that process and see which one actually looks like a phrase that you're interested in reading, then you know exactly what that secret message was supposed to be. So it sounds like a lot of work, but cycling through 600 times for a computer takes essentially no time at all. So in terms of actual security, it's complete trash. Okay, so as I mentioned earlier, I do want to quickly cycle back to that piece of code that I showed you last time, which is going to be right in here. Okay, so what I did last time is I took my word M-A-T-H, and I scrambled it up with using this little bit of code. So what happened is I took those letters, converted them to numbers. Those numbers got scrambled with my function f, and then I converted them back to letters. So now I'm sitting with this phrase UKPF in my scrambled command. So what I'm going to do is I'm going to basically do the exact same thing, but now with a new function g, which is that little inverse that we just got done building, this 9x plus 14. So feeding that phrase UKPF into that thing, if I run this thing, it does bring me right back to the MATH. So as I mentioned earlier, what you could do, kind of to brute force this thing, is you can take this piece of code and put this inside of a nice little loop that's going to reshuffle the deck on what f is supposed to be. Initially, f could be a 3x plus 10, and then index the 3 into a 4, into a 5, into a 6, into a 7, and then 10 into an 11, 12, 13, 14, and see all the printouts to actually kick out what those phrases are supposed to be. I'm going to probably give you a nice little bonus one on your next activity that you can dabble into that world if you're interested. Afterwards, I'll show you my brute force attack on that thing so you can actually see the kind of cutesy little CS lingo that comes out as your final answer. It's kind of a fun little one to play with. I'm not going to force you to do anything like that, but it is worth kind of exploring into the coding side if you're interested in doing so.